Good morning, everybody. This is the Facebook workshop, Delivering Media for Billions. And not only are we honored to have Facebook presenting this workshop, we're also extremely grateful because they're our diamond sponsor. So without further ado, I'd like to hand over to Nick Wu, who will chair amongst the participants of Facebook. So thanks again, and on with the presentation, Nick.
Thank you, Paul. Would you be able to let me do the screen sharing?
Yeah, it's about now.
Cool. All right, welcome everybody to the Facebook workshop at the PCS 2021. I'm having a really great first day. I'm hoping you are having the great first day as well. So this is the Facebook workshop. We're going to talk about how we deliver media for the billions. So this is my name is Nick Wu. I'm going to talk to you about video at Facebook. What does that look like? And Chema and Nicholas would then go and tell you about real-time calling on special hardware devices. And then the team will tell you how do we optimize compute with machine learning and the benefit cost model. And finally, Denise will share how do we optimize the mobile playback experiences with visual quality metrics, and followed by the Q&A at the end. So I'll be collecting the questions throughout the session, and then we'll do the final Q&A at the end. Cool, so let's get started. So this is Facebook. So we are the largest social network with over 2.85 billion users. We have a wide range of products. We have social networks such as Facebook and Instagram. We have messaging apps such as Messenger and WhatsApp. We also have hardware devices such as Oculus can let you experience virtual reality and augmented reality. Portal devices for you to connect with your friends and family at home. And also have workplace product that you connect with your colleagues in the workplace. So we have a wide range of video products among all these different products. These are just some of the examples. So from the left to the right, so we have like live sport. You can watch live sport on Facebook. You can also watch a premium music video for your favorite artists or bands. You can also create now a short form video via Reels. And in a typical messenger call with your friends or family, now you can also watch a video together in a call. And besides that, now you can actually schedule and open a room to with your friends, family, and people who have similar interests. And you can even go live and broadcast the conversation that's happening in the messenger room. So at Facebook, our mission is to let people have the ability to build a community and bring the world closer together. And this is an example of how we are bringing the world closer together. So there's some statistics from last year's New Year's Eve. So on the New Year's Eve 2020, that day, we have 1.5 billion voice and video calls made globally on WhatsApp. This is the most ever calls in a single day. And also, on the same day, we have 55 million live broadcasts across Facebook and Instagram globally. So at this kind of scale, there are a couple of key problems we're looking at. So we want to increase the video efficiency of a video. We want to reduce the compute requirement and energy footprint. We want to reduce the storage footprint as well. But at the same time, we want to offer high stability and reliability and near infinite scaling. But since this is a billion scale, this actually really dictate many of our choices. And today, these talks are going to share some of the choices and design we made to address this problem. So first, we're going to have the real-time communication. We're going to talk about efficient resource allocations. We're also going to talk about the optimal playback experiences. So with that, I'm going to hand over to our first speaker, Nicholas and Gemma.
Thanks. Let me kick off screen sharing. Here we go. Hi, my name is Niklas Enbom, and I work on Facebook Portal at Facebook Reality Lab. I'm an engineering manager at the Portal calling platform team, and I'm here together with Chema Gonzalez, a software engineer who's our current technical lead for Portal audio and video quality for calling. Our talk today is focused on what we can do differently when building a calling solution for specific hardware compared to a generic software appliance for Android or iOS. Portal is Facebook's ambient computing platform, focused on building close connections between friends and family, leveraging Facebook, Messenger, WhatsApp, Instagram ecosystem, as well as technology from our AR/VR partner teams. Let's go a little bit into how Portal differs from other calling devices. At the core, this is an Android device based on similar hardware as a mobile phone. Let's look at what differs. Portal has much better support for hands-free calling, using up to 8 microphones to capture audio from far away with high quality. We can also combine that with camera information and use beamforming and zoom in on faces, things like that. Unlike generic software clients, we can also tune the audio processing directly for the hardware we're running on. Portal has a high-resolution camera combined with AI processing to automatically zoom in and capture people even if they move around the house. The high resolution makes it possible to deliver HD quality even when zoomed in without any interpolation. Portal has a larger screen, making calls more immersive. But this is also a challenge because this increases the requirement and expectations on video quality, since any degradation will be more visible. However, the environment is different compared to a cell phone. We can leverage the fact that we're always on Wi-Fi, which means we have higher bandwidth and better connectivity, and we don't have to worry about things that happens on the cellular network. We're also plugged into power, so we're much less constrained when it comes to power used compared to a device that runs mainly on battery. Now, Chema will talk a bit more in detail about what we do to deliver higher video quality for our calls.
Yeah. So let's discuss some of the specific hardware optimizations. When you think about the Portal, you first start with a series of deficits. We are running Portal on a mid-range mobile SoC. We have a very large screen, which creates an expectation of good quality video and audio. In order to do that and to support the smart camera, we actually have a relatively complex video path, including AI and smart camera processing. We also support video and audio effects and an application called Storytime that allows you to do this type of video effects. And finally, there's another major issue, which is when we realize Portal users are way more likely than vanilla Messenger and WhatsApp users to do group calls, which means we had to support simulcast and multiple recorders from the beginning. So these are the main challenges for Portal. The main advantages is, unlike most applications, we only support 5 devices, which are the 5 different portals. And even for those 5 devices, we only have 2 different SoCs. We have control over the whole system, including our AOSP fork, the Linux kernel, the OMX layer, and some of the hardware layers, including the video and audio processing pipelines, both uplink and downlink. Next slide. So the first optimization in order to do high quality calling is you need to use the hardware codec of your SoC. This is actually a requirement, basically a requirement in order to do high definition video calls, because it saves a lot of CPU, including for group calls. But apart from the CPU savings, every other thing that comes with the use of hardware codecs, and in particular the hardware encoder means challenges. So most encoders are a vendor-specific black box implementation. Encoders on SoCs are typically designed for camera video recording, not for real-time communications. Things like rate control, rate changes, the IP frame size ratio. And this is like any optimization or any actually use of the hardware encoder is something that you probably cannot do across all cell phones. We're talking about Android here. Really. So that means, because it's not only that you actually need to test for specific phones, you actually need to test for specific SoCs and phones. So let me give you an example of that. We actually got 2 devices, right, based on the same SoC, the Samsung Snapdragon 855. And we just checked their HEVC, or also known as H.265 hardware encoder. Here on the x-axis, you see different actual bit rates, from 500 kilobits per second to 2.5 megabits per second. On the y-axis, you can see a quality score, in this case VMAF, where higher values means higher quality. In blue, you can see the results for a device based on the 855, the Google Pixel 4. In orange, the same results or similar results for a Samsung S10. And you can see between 500 kilobits per second and 1 megabit per second, there is a significant quality difference for the Samsung S10 phone. We know the difference for this is likely to be the OMX tuning, which is something that we actually had to do a lot. Next slide. The good news about Portal, as mentioned before, is we have control over the hardware encoder, including OMX access. We work on multiple optimization and fixes on the OMX layer, from things from the QP ranges on 265, FRLR brokenness, and other issues that you actually need control over. Next slide. The second thing that we actually did is we measure the quality of our encoders. For example, in this axis, you have a similar graph to the previous one, but in this case, what we are comparing is for our SoC, what's the quality of our three encoders. Our SoC comes with three hardware encoders, HEVC, AVC, and BP8. Here on the x-axis, you see again bitrate from 0 to 2.5 megabits per second. On the y-axis, you also see the same quality score. Again, higher is better. You can see here that the blue line, which corresponds to HEVC, provides better quality, which means that our HEVC encoder is actually better than our other two encoders. The main issue of HEVC, also known as 265, is that there is no upstream support on WebRTC, so we had to build around. Next slide. Another optimization required for good performance is the use of texture encoder and decoder. The Android Media Codec has two APIs for access to both encoder and the decoder, byte buffer and texture. Texture is a requirement for decent performance on HD video for many reasons. The results, for example, in some of our experiments, when we're trying to increase the knob of CPU usage by using a very heavy augmented reality mask, the use of texture encoders and the use of texture in both encoder and the decoder managed to move the performance from 15 frames per second to 20 frames per second, which is definitely noticeable. Next slide. Another optimization that you need to consider when working with hardware encoders is the operation of the different resolution and frame rate scalers. These are the modules that allow you to tune how to control the hardware encoder. Again, the problem here is the encoder. The decoder is much easier. So we know that for a given bitrate, you can choose a given resolution, a given frame rate, and then you get an effective bitrate. There are 4 or 5 different controllers on WebRTC, and what we actually found is that first, they are mostly tuned for software encoders, not hardware encoders. And also sometimes more than one actually work at the same time, which means that they actually work against each other. To give you an example, we actually found an issue where the frame rate scaler was actually colliding with hardware bitrate adherence in the following way. Our frame rate scaler was thinking that we were sending too much data, and then at some point start starving the encoder from 30 to 15 frames per second. Our hardware bitrate, our hardware encoder responded to that by doubling the size of each frame, which basically means we have worse video and absolutely no benefit. You have to be very careful with this. Next slide. Finally, let me discuss some optimizations for the environment, in this case, based on network. First, because Portal typically uses HD video, it normally uses higher bitrate than most applications, which means that you have to be able to ramp up faster than vanilla apps. That means we do both initial and mid-call probing. Second, we're talking about codec adaptation. We actually found that the quality, also known as QP scaler, works actually pretty well with hardware encoders, as it minimizes resolution changes. Another optimization is we know that Portal only works on Wi-Fi, which means that our connectivity is better and we can be a little more aggressive. Finally, one more issue is one of the selling points of Portal is that you can connect to any device on the wall that has either WhatsApp video or Messenger video, which means we have a huge remote client diversity. And that means we had to implement simulcast from the beginning. Next slide. Let me talk about two interesting push limits optimizations we work on. The first one is ROI encoding, region of interest video encoding. The idea of region of interest video encoding is put more bits wherever people cares. For example, you can see here in this image, we actually mark the blocks around the human face, the stick figure face, in different color, because most people will actually care more about how the face looks than how the rest looks. The idea is relatively simple. There are lots of implementation challenges. First, encoder support for ROI is mostly broken or incomplete, especially the OMX implementations. So you have to actually fix them and finish them up in some cases. ROI has a negative effect on rate control. Next one, it's ROI has a minor effect on encoder latency, increasing the encoder latency. And the final challenge is we're still not pretty sure how to measure the benefit, right? Because at the end, if you need a number to justify that this makes sense, it's relatively hard in terms of any of the quality measurements like VMAF, PSNR, or SSIM. Next slide. The last thing I'm going to discuss is our effort on latency reduction. We know that end-to-end latency is an important feature for natural conversations. If you increase the latency between the users, they will actually find the conversation weird, but they will not be able to pinpoint the problem. We know that the current portal latency is on par with other Android calling applications. We measured that. And we actually work on two main audio latency optimizations and video latency optimizations, but particularly the work we've been doing so far has been on audio. The first one, we actually reduce the audio packet size. Basically, we are sending more packets, but packets are smaller, and we limit the amount of packetization on the network. And second, we actually are moving our Android backend API from Java Audio, which is a vanilla thing that everybody uses, to A-Audio. We understand this is actually very hard to make work across other set of large mobile devices, but again, because we only have 5 devices and 2 SoCs, this is something we can afford. The last one is we're working on disabling audio-video synchronization. Nicholas?
Thank you. Here we go. Cool. So I'll spend some time to talk about how we measure the impact of these different items we're working on. Traditionally, Facebook relies heavily or even solely on user experimentation to measure improvements. With Portal being a new device, and maybe more important, it's a device that people pay money for to get. We can't just rely on field metrics and run experiments. Instead, we operate at 3 different layers. First, we do offline analysis. Secondly, we do real-time lab testing. And the last step is to get user data. The offline tools we have generated, they have generated the graphs Chema showed earlier, for example. We have developed a tool to profile hardware encoders, which we use both to tune our settings as well as to compare codecs and evaluate new hardware platform. We also have a lot of tools developed to analyze RTP streams as well as encoded video bit streams, used both for testing and troubleshooting. A lot of our tools are open source, both for helping others to use them, but it also makes it much easier to collaborate with, for example, a hardware vendor if you want to solve a quality problem. For those of you that haven't worked at a large company before, it's also very hard to take something that is closed source and make it open afterwards. It's much easier to have it open source from the beginning. Next level is real-time testing on actual hardware devices. We have added recording and injection hooks in our WhatsApp and Messenger clients that makes it possible to compare source data to receive streams on the other end. We can also capture the encoded stream for analysis. With these captures, we use sort of fairly conventional tools to evaluate quality. We use VMAF for video, for audio, we use Viscol and Polka. For non-referential video quality, we use a tool we call Brave, which is built on top of Brisk, but we have added in a factor for temporal smoothness. As mentioned, these tests we can run on actual hardware in real time, and we can also run them with simulated network impairments, adding bandwidth limitations and packet losses. They're also integrated in our test automation system, meaning that we can run them every day and catch any regression very quickly. Last step is the more conventional Facebook way to gradually expose a feature and measure its impact. Here we rely on similar metrics as other calling clients, call duration, quality ratings, etc. Here is a quick summary of essentially how portal calling differs from mobile client calling. I hope you found this presentation interesting. Chem and I will be happy to answer any questions at the end of the workshop. Now I'm handing over to Tain.
Hello, everyone. My name is Tain Kim. I'm a software engineer at Facebook. Today, I'm going to talk about how Facebook maximizes visual quality using benefit cost model and machine learning. Problem statement is Facebook uses ABR to reduce buffering. And in order to produce ABR, we have to produce multiple encodings for one video upload. And we also have many combinations by recipe, I mean different codec options. So for example, H.264 or VP9 or AV1, or different configuration for each one of those codecs. For example, advanced codecs such as VP9 has a better compression efficiency over older codecs such as H.264, but it requires a lot more compute to produce it. Facebook doesn't have enough compute resource to produce advanced codec for hundreds of millions of video uploads every day. So the goal is to maximize overall user experience using fixed compute capacity. In order to achieve that goal, we made a few observations. First observation is we only and we then we can deliver it as many times as we need without incurring any additional compute cost. Another observation is there's only a small percentage of all videos on Facebook that generate the majority of watch time, which means the watch time distribution is extremely skewed. There are many videos that don't get any watch time or get very little watch time, whereas there are a very handful of videos that dominate the overall watch time pie. And the reason why Facebook is limited on the compute resource is because our data centers have limited amount of energy that we can draw from the main grid. So we cannot draw infinite amount of energy from the main grid. So in order to maximize everyone's video experience within the available power, we need to apply more compute-intensive recipes, such as VP9, to most watched videos first, before applying them to relatively lower watch time videos. This is the visual illustration of that observations. So we have two videos, video A on the left-hand side and video B on the right-hand side. Both videos was uploaded at 5 megabytes. And let's say video A has a 1 viewer, whereas video B has 100 viewers. Now let's assume that we spend one CPU unit to produce more advanced encoding for both videos. And advanced encoding retain about the same visual quality. Now the compressed video A has a 3 megabytes, and it was able to save one user about 2 megabytes saving. So one user had to download 2 megabytes less for the same video. Whereas for video B, we applied the same CPU and we were able to reduce the file size to 3 megabytes, so same as video A. However, that 2 MB saving for the video is multiplied 100 times for 100 viewers. So in this case, when we have a compute constraint, it makes sense to apply advanced encoding on video B first before doing it on A. The way we implement this is by using a benefit cost model. So we assign priority values to each encoding job, and we have a sophisticated encoding worker farm that process those in priority queue manner. So that means the job with the more urgent priority are processed first. We express this what we want to do in this formula. So the priority is calculated as benefit divided by cost, and benefit is defined as PD rate, the specific quality level. Think of it as like normalized quality level, and multiply that by how much watch time we think the video is going to generate. So like how much how many seconds the video is going to be watched in the future. The cost is defined as the normalized compute cost of encoding job. So like how many CPU milliseconds that we think the encoding job requires to finish. So if we frame the priority, benefit, and cost this way, then basically we are telling the worker farm to process to optimize for the benefit throughput given our compute capacity. So in the previous slide, I mentioned we predict how much watch time a video is going to get. And because we don't have ability to see future, we rely on machine learning model to predict it. So we don't predict far into the future. We only predict how much watch time a video is going to get in the next 1 hour. And our team specializes in encoding system. We don't specialize in machine learning. So and then Facebook has a lot of machine learning resource. So we partner with our video data scientist team to develop this model. This model, while we were training it, we used the 2 sets of features. The first feature is video features, and this set includes past watch time, so how much watch time a particular video received in the past, and other video metadata such as duration, how long the video is, and post type, like where did this video come from? Is this from live or stories or just regular upload? Second set of features are user features. So how much time users' older videos were watched in the past, and also users' potential audience size. So how many friends or followers they have. And we have 2 different set of machine learning model. One we use at the time of video upload, and then another one when the video is watched by user. By having those 2 separate models and call them in 2 different time, we are able to actually optimize, like identify videos that's going to get watched a lot at the time of upload and produce more advanced encoding sooner. And also there are some videos that are uploaded by owner that have a few friends or followers, but then the video go viral maybe a week or 2 weeks after they are uploaded. And because we are relying on video features and the machine learning is online model, we are able to detect, okay, it's gaining watch time rapidly. Therefore, we want to prioritize advanced encoding for this particular video. So we are able to do both by using 2 separate models. The end result of this work had several positive outcomes. The first is we were able to shift a large portion of watch time to advanced encodings. Remember, advanced encoding has a better compression efficiency which means we are able to reduce the bit rate as similar or better quality. And also, what that means is users have to experience less buffering because they are downloading fewer bytes. And also that will translate into allowing people on Facebook with a limited data plan, think of emerging market, to watch more videos at better quality. So in the United States or in other countries, unlimited data plan is popular and common. However, in some emerging market, people have to pay for, say, 2 gigabytes in their cell data plan. And within that limited plan, we are able to, people are able to watch more videos because they have to download fewer bytes. Second positive outcome is it's mostly more geared toward our internal engineers. We no longer have to manually define priorities when we launch new recipe. And Facebook heavily invests in recipes to improve user experience. So every time we do that, engineers had to, in the past, had to figure out the static priorities and figure out, does it make sense to produce this more expensive recipe for this particular video? And it was very, very, I guess, manual intensive work. And we had many lines of such static rules. Now, because you just need to define benefit and cost, and those are collected automatically while recipe is in experiment phase, engineers don't have to do much when they are launching a new recipe. Third positive outcome is this makes the system more reliable. We sometimes lose power in our data center due to power outage. Maybe think of like tree falling into power line, or something bad happened to our data center. And that means we have a reduced capacity while those data centers come back online. Because we are using this model, because we are doing the most important ones first, we are able to reduce the impact of a reduced capacity. So it improves the reliability of our encoding production process. The publication. So recently we published a Facebook engineering blog named How Facebook Encodes Your Videos. And this is a longer version of the talk that I just gave. So if you are interested, please go check out the blog. You should be able to find it on Google. Thank you. And now I'm going to pass it on to Denise.
Hi, my name's Denise Noyes. I'm an engineer at Facebook on our video infrastructure team. My team is responsible for our video quality of experience. We decide, given the device constraints and network conditions, what the most appropriate video quality is to download at any given point in time during video playback. Today, I'll be talking through how we use video quality metrics to make smarter ABR decisions. First, I'll talk about which visual quality metrics we use when we make quality decisions during playback. Next, I'll talk about how we use these visual quality metrics to inform the constraints that we place on the qualities that we consider during our ABR decisions. Next, I'll talk about how we also use these quality metrics to inform our quality selection algorithms. And finally, I'll touch upon some future work that we're considering in this space. The visual quality metric we currently depend on for our quality decisions is Playback FBMOS. Playback FBMOS is a full reference metric that measures the quality preserved by our video processing pipeline between the uploaded Facebook original content and the encoding delivered to the viewing device. For most of our content, this ends up being a linear interpolation of SSIM. This score also scales to the viewer's viewport device. So if you look at a particular encoding, the 720p encoding Playback FBMOS score might be higher when viewed on a smaller viewport device and smaller when viewed on a larger viewport device. When we use FBMOS in our quality decisions, we want to keep in mind the acceptability and annoyance thresholds. If you look at this on the slide, you see at the bottom we have the red not acceptable range. So here quality is not sufficient to meet user expectations, and it may bother them enough to stop watching. In orange, we have annoying but acceptable. It's not sufficient to satisfy their expectations, but it probably wouldn't cause them to stop watching. And finally, in green, we have not annoying. So basically, the quality is satisfactory for user expectations. So when we think about the quality being low enough to be in the red range, not acceptable, it might be worth accepting a slightly higher risk of stalls to achieve better quality and at least bump it up to the orange range, for example, as long as the network still has a reasonable chance of supporting that quality and at least bump it up to the orange range, for example, as long as the network still has a reasonable chance of supporting that slightly higher bit rate. On the other hand, if you look at the not annoying thresholds, there might still be value in trying to fetch an even higher quality, for example, going from 720p to 1080p, but we have very little tolerance for increasing our risk of stalls to achieve that higher quality. Now I'll talk about how we use quality scores in our constraints. Despite using network conditions to make our quality decisions, there are times we may want to cap the maximum quality we consider for automatic selection. One major constraint we have is avoid on cell. There are times that when the user is watching content on a cellular metered network, we want to limit the maximum bitrate that we'll play. One reason here is that data can be expensive, and the cost of that data typically is market dependent and varies a lot from country to country. And we want to be able to have a system that can be dynamic enough to account for those costs. Next thing to consider is that we have a very diverse ecosystem of content. We have everything from highly produced Facebook originals. We have a lot of user-generated content uploaded and captured from mobile phones. We do a lot of live streaming, including gaming live streaming and even popular sporting events. And we need an approach that works for the variety of content that we have. And we want to ensure that we maintain a consistent minimum quality bar across the diversity of content that we support on our platform. We also want to limit the maximum quality we prefetch before a video is on screen. For Facebook's feed-based architecture, we want to have the first few seconds of content cached on disk ahead of time to achieve low latency startup times for our videos. However, we also want to minimize wasted bytes for content which isn't ultimately watched, and especially on less powerful devices, minimize the CPU pressure caused by decoding higher bitrate content. So again, here we turn to MOS-based limits to cap the maximum quality that we consider. Now let's look at some sample videos to discuss how we define the constraints we just covered. In this graph, we have bitrate on the x-axis and FBMOS on a scale of 0 to 100 on the y-axis. The blue line represents the encoding curve that we might have for a less complex encoding, while the orange line is the curve that represents a more complex video encoding. So if, for example, we used a bitrate-based limit, for the sake of argument, let's draw that line at 500 kbps in red. You can see that each video would get limited with a much different visual quality. So here you would have the blue video would have a pretty reasonable MOS score of about 85, whereas your orange video would drop down to something closer to 38, which is not amazing. So choosing a strict bitrate limit could result in a pretty large quality gap depending on the complexity of the content and where your encodings are cut across the bitrate spectrum. Instead, let's look at what would happen if we set up limits by MOS given some bitrate guardrails rather than purely looking at bitrate. So in this example, we have the same bitrate versus quality graph using the same orange and blue videos we discussed earlier. And now we've added some vertical lines which represent our bitrate guardrails and some horizontal lines which represent the quality thresholds that we're trying to achieve. The green line represents the hard minimum and the yellow line represents the soft maximum. So here we want to allow the maximum soft cap on the quality that we play needs to be above that green line without having multiple qualities above the yellow line. So in this case, that would end up with a bit rate of about, say, 200 kbps for the blue video with a Facebook MOS score of 80, and something closer to 750 kbps for the orange video with a FBMOS score of 60. So they're still not perfectly matched, but the gap is a lot smaller than what we saw before using a purely bitrate based thresholds. And if we rely so much on quality scores, I also want to talk about why we have these bitrate guardrails. So we believe that the quality scores are more representative than just looking at resolution or bitrate, but we also know that they're not perfect for every single piece of content in our ecosystem. Therefore, we want to define some guardrails based on bitrate to make sure that we don't naively cap quality too conservatively or let it grow too aggressively to, say, be something like 10 megabits per second. So we're able to define bitrate guardrails to kind of protect ourselves from either of those extremes. In the last section, I talked about the constraints, and now I want to talk about our actual quality selection algorithms. So when we talk about applying these soft caps, it doesn't mean that that's the quality that our player will necessarily choose to fetch. It just means that that's the maximum quality that we'll consider, but we may choose to go lower based on network conditions. So to start, I want to talk about thinking about penalizing overly bad quality. And how do we make sure that we don't choose quality that's too low by being overly conservative in our quality selection algorithm? So we have times that we want to introduce a lower bitrate lane for devices that might be on worse networks. But we want to make sure that when we introduce those lower lanes, we don't necessarily be so conservative that we overplay those low qualities, and instead we save them only when we think that they're truly necessary. So we define this definition of low quality using our Facebook MOS scores. So we have an algorithm that balances the buffer buildup with risk factors like encoding and bandwidth variation. And we basically decide to make our algorithm more aggressive to try to reach a minimum playable quality, and then a little bit more conservative when it's above that minimum quality bar. And we found that this lets us balance out introducing low bitrate lanes for users whose networks truly require it without regressing the quality of users whose networks are actually not poor enough to require that low bitrate selection. Next, I'll cover making quality decisions at the higher end of our quality spectrum. Again, for reference, here's another graph of our visual quality on the y-axis and bitrate on the x-axis for a hypothetical encoding. It's a pretty typical bitrate versus quality curve where you can see that the bitrate to achieve the next quality jump roughly doubles with each point in the encoding ladder. So by way of example, we used to have a ceiling on about 2 Mbps for the maximum bitrate that we would serve to our mobile devices. But we wanted to be able to raise this because we know that there are many devices and many networks that could actually support and would benefit from a higher quality. At the same time, we don't want to meaningfully regress stalls just to achieve that higher quality. We want to make sure that that higher quality lane, so for example, let's say going from 720p to 1080p is available for users whose devices and networks can support it, but we're not so aggressive about trying to increase that quality that we risk stalling when we think that there is actually a chance that we might not be able to support that higher resolution. So we launched this risk-reward algorithm to be more conservative about choosing the highest bit rates unless the gain in Playback MOS was meaningful. We compute the risk and reward for a format by comparing its bitrate in FBMOS with the immediate lower format in the bitrate ladder, looking at the delta between the bandwidth estimate at each point and also the bitrate for each of those lanes. The risk is the increased risk of stall, which we represent in terms of the relative difference of those bit rates and bandwidth estimate, whereas the reward is the gain that we see in increase in FBMOS. So we calculate ratios based off of these different metrics, and when the gain is high enough and the risk is low enough, we'll consider increasing the quality for the user without regressing stalls. To wrap up, I want to briefly discuss some future work we're considering in this area. Currently, all the quality scores that we're looking at are the Playback MOS, which represents the delta in quality loss from the originally uploaded content to the encoding that was played back. However, we also need to consider the absolute quality of the content. So for example, you might have a video that was uploaded at say only 500 kbps and played back perfectly, or you might have a video that was originally uploaded at 50 mbps and then there was more quality loss at the playback side, but the actual overall quality was higher. So we need a better way to incorporate the overall quality, not just looking at the quality loss during playback. We also have a lot of limits which are defined by these hard-coded thresholds of what's acceptable and what's not acceptable. And we need a more dynamic, less threshold-based model for how to capture more gradation in that experience. And finally, we want to do more research into the user's acceptability and annoyance thresholds. We have rough approximations of what we think that they care about, but we know that it varies a lot based on a lot of contextual factors in their viewing experience and the type of content that they're consuming. And this is an area that we want to explore further. So with that, I'm going to wrap up, but we will have some time for questions following the end of this workshop. Thank you.
Well, thank you, Denise, for the great talk. And then that's welcome everybody back for the Q&A session. And then we have a list of great questions lined up for our talks and for the industry in general. So I'm going to start with one of the first questions that posted here. The question here is, what is the maximum end-to-end latency that enables an acceptable interaction between audience and the host in the live streaming session? So I think there's a couple of different things to answer here, but maybe Chema or Nicholas can answer from the RTC standpoint.
From the real-time, here's Chema. From the real-time communications, there are a couple of standards, but ITU defines 150 milliseconds on one way for real-time, 150 milliseconds or lower to be good, between 150 and 400 to be okay, above 400 to be bad. In terms of broadcasts, I'm not positive there is a bound.
Awesome. Yeah, I think that's great. So but there are a couple other questions, I think, on Portal as well, so I'll just go with that first. So about Portal, what is the range of frame rate and resolution that you use as a basis? Do you do both upscaling or only downscaling?
So our frame rate is up to 30 frames per second. Our resolution is up to 720p, which is 1280 by 720. And the last question is, the answer is we do not do upscaling on the sender side. We only do downscaling.
Awesome. Thank you, Chema. So the next, I think there's another Portal question. Let me just quickly read that as well. So for real-time calling, we use ROI encoding for the face detection. So have you considered complementing this with foveation tracking, prediction, and or saliency?
Cool. I can try to answer that. So I interpret that question as like we would be using the receiver's gaze direction to control our encoding quality. So essentially, you get higher quality based on what you are looking at. And the simple answer is no, we haven't looked at that. It would be cool to explore it for sure. I mean, I'm not sure if the feedback loop is fast enough to make this work. But whoever asked the question, whoever is listening, come work for us and let's build that together, or come collaborate with us to explore it.
Yes, excellent. Yes, we are hiring, and then we'd love to collaborate with you on all kinds of ideas. So the next question, I'll answer actually the two questions that they're similar, so I'll take that question, answer them together. So one of the question is, the Facebook team start experimenting AV1 along with H.265 and VP9, and the other question is, I think is related, is basically there's a lot of conflicting publication on video codec, energy impact, and footprint. What is your view on it? So I'll take that two together. So for AV1, so Facebook is actually part of the founding member of AOM. So we're invested to make AV1 more successful through improvements and investment in coding quality, and as well as the computational complexity reduction. We have worked in the software implementation working group in AOM to reduce the computational complexity. So yeah, we are invested to make AV1 successful. And then also Taim's talk was just like addressing about this, how do you trade off this the benefit and the cost? So this is also addressing this same topic as well. Yeah, and then we have constantly experimented all kinds of codecs, software, hardware. We have also announced we have this Mount Shasta program that we can use the hardware video codecs. So computational reduction is definitely a big part in energy impact in our plan in our data center. All right, let's move on to the next question. So I think the question is probably for Taim. How do you automatically assign priorities?
Sorry, can you say it again? How do I assign?
How do you automatically assign priorities?
So we trigger encodings at 2 different times. When video is uploaded, we predict the watch time of that particular video, and also for each encoding job, we know which recipe it's using, and based on the recipe, we can estimate what kind of ED rate it's going to end up when encoding is produced. We also rely on historical CPU data for that particular recipe, and we merge it all together and able to calculate the benefit and cost. And based on that, we calculate the priority, and we actually assign priority per encoding job. And we don't know anything about what other jobs we have. We just put it into the priority queue. And our backend worker farm actually fetch from the priority queue based on the priority. So it's fairly, that's how it works today.
Awesome, thank you, Dane. Let's see. So there's another question here. Okay, so this next question I think is for Denise. I think she's here with us. The question is, do you use FBMOS scoring at the title level or at the lower level?
Hey, so each of our videos has multiple encoding families, for example, an H.264 ladder and a VP9 ladder, and then each of those ladders have different encodings at different resolutions. So when we look at Playback MOS from the player side, we take the MOS score for a specific encoding. So for example, the VP9 720p encoding for a specific viewport. So even say the 720p lane will be sent in the manifest as an array of scores for different viewports. And then depending on the viewer's actual viewport and their device size and the context that they're watching it, we'll interpolate the correct score and use that in our calculations. So we'll get basically a range of scores for each point in the encoding ladder that we then interpolate for the viewer's actual viewport size.
Awesome, thank you, Denise. I think we have a couple other questions here. Let's see. There's another question. Is error resilience a real issue for your products, or are you happy with current network QoS levels? I think this can be answered by all of our folks. So who wanna take a shot at this? Sure.
So I can give the view from a real-time communications point of view. The answer is on real-time communications, we definitely need to support a very large diversity of networks, and we cannot choose who the customers talk to. For that, we definitely do network adaptation to try to limit the amount of losses on the network. And we also do both audio and video resiliency on the receiver and the sender.
Anything on maybe on the playback side, Denise?
Yeah, we definitely have to make sure that our players are resilient to various network errors. So we have a sense of what type of errors are retriable and what type of errors are potentially fatal. And if they're fatal, for example, at one encoding lane, it's possible that we might be able to recover by switching to a different lane that is available on the CDN, for example. So again, it depends a lot on the type of error, what our exact fallback strategy is, but we've definitely invested a fair amount in trying to recover as quickly as possible from various failure scenarios, either on the client side or on the server side.
Awesome, thank you, Denise and Gemma. I think we still have a couple of questions. So this question is, do you get real world feedback on video quality? And then to see how it is actually performed in real world scenarios.
I can take that one again if you'd like. So we have the benefit of scale to be able to do a lot of A/B tests. Our A/B tests will definitely illustrate how user behavior changes, like in reaction to different ABR strategies or different encoding changes, which is great because we can see, are they watching more content? Are they giving up? Are they stalling more? What we don't get is a lot of high volume data on, is this quality actually acceptable or not? We kind of have to infer that from their user engagement. On the other hand, we do have a few other lower volume feedback mechanisms as well. So there's a way for users to report bugs to us and basically report errors in the app. You can just like shake the phone really hard and it actually submits errors to us. So we are able to monitor feedback that way. We occasionally do surveys and we also collaborate with the research community. So we have work that we're doing with different universities around the world to get a deeper understanding of how users react to different qualities in a lab environment, where we can actually have a much more controlled setting and understand kind of what matters to our users.
Awesome. Thank you very much, Denise. Yeah, so I think that's all the question, and then so we're gonna wrap up here by so please come by our virtual booth on the Huawei platform. So we are happy to interact with you, answer all your questions, and then you can feel free to reach out to us for more details, and we'll definitely look for more collaborations. And thank you all for attending our workshop. And with that, I'm gonna hand it back to Paul.
Well, thanks so much, Nick, and thank you so much for Facebook for sponsoring and giving us the diamond sponsorship. And I'd just like to say I've got a couple of seconds to go. I'd like to advertise the wrap-up session in 20 minutes with Dave Bull, an overview briefing, and there's some networking going on now on GatherTown. So if you look for the links at the other network times. So thanks everybody, and goodbye.
Bye.
Bye.